The bulldozer. The bulldozer is the machine that levels the ground everything else stands on. At the extreme end of the category, production bulldozers weigh 152 metric tons, carry a blade 24 feet wide and over 9 feet tall, and produce 1,150 horsepower from a turbocharged diesel engine. A single pass moves enough soil to fill 6 standard dump trucks. The operator sits at the height of a second-story window. The blade does not simply push soil forward. It rolls material into a continuous moving wave, increasing carrying capacity per pass compared to a flat push. A specialized undercarriage allows the tracks to conform around ground obstacles, maintaining constant contact with the surface and distributing 152 tons across a footprint wide enough to prevent sinking on unstable ground. In coal fields and iron ore pits, one machine at this scale performs the work of 3 to 4 standard bulldozers. The ripper mounted at the rear penetrates earth hard enough to break stone that blasting is too dangerous to touch near populated areas. The heavy forklift. The heavy industrial forklift operates on a scale that places it closer to a mobile crane than a warehouse tool. Lifting capacities reach 85 metric tons. Its tires stand taller than a giraffe. In a single lift, it raises the weight of 10 adult elephants to working height. The engineering challenge at this scale is not raw force but control. Variable load sensing hydraulics detect weight automatically and adjust oil flow for millimeter-level precision because a wind turbine nacelle or a freshly cast steel slab cannot be nudged back into position after a misjudged approach. These machines project a blue warning light onto the floor around them because at their operating weight, audible warnings alone are insufficient in the noise environment of a steel mill or port. Without this category of machine, assembling wind farms would require expensive crane barges for every component transfer. The heavy forklift converts a multi-crane operation into a single vehicle task. The bridge launcher. The bridge launching gantry weighs 580 metric tons, stretches 91 meters end to end, and assembles a bridge from the top down without any equipment operating at ground level. It travels along the top of the bridge it is already building, carries a full-length concrete girder inside its frame, extends itself forward across the open void between 2 pillars, and lowers the girder into position. Its 64 wheels rotate independently, allowing the entire machine to drive sideways without any turning radius. Workers access the underside by descending from the deck like climbers hundreds of feet above a valley floor. Because the gantry operates entirely above the ground, no construction roads are cut through valleys and no forests cleared for crane staging. The machine holds its own mass and the mass of a full concrete girder suspended over open air, relying entirely on the rigidity of its frame and the grip of its forward anchor to prevent overturning. The mining shovel. The hydraulic mining shovel sits at the outer limit of excavation. At maximum scale, these machines weigh over 1,000 metric tons, run on 2 diesel engines, producing a combined 3,000 kilowatts, and carry buckets holding between 52 and 70 cubic meters per pass. A single scoop lifts the equivalent weight of a fully loaded commercial aircraft. The machine burns over 1,000 liters of diesel in a single operating day. A full dig and swing cycle completes in under 30 seconds. At the operator's eye level, standard pickup trucks on the mine floor below are not visible. These machines are designed to fill a 400 metric ton haul truck in 4 to 5 passes, running around the clock in oil sands, iron ore pits, and copper mines in temperatures ranging from scorching heat to well below freezing. Moving more material per scoop with a shorter swing time is what makes deep open pit mining financially viable at the volumes modern industry demands. The haul truck. The ultra-class haul truck is the logistical partner to the mining shovel. At maximum scale, it carries 450 metric tons of payload, runs on 2 diesel engines, generating a combined 4,600 horsepower, and rides on 8 tires each standing nearly 4 meters tall. The truck itself weighs 360 metric tons empty. Gross vehicle weight when fully loaded reaches 810 metric tons. The drivetrain uses diesel-electric technology, the same principle found in locomotives. Individual electric motors at each wheel provide torque control that pure mechanical transmission cannot match at this scale. A single set of tires costs hundreds of thousands of dollars, and a sharp rock on a haul road can destroy one in minutes. Standard passenger vehicles traveling behind an ultra-class haul truck are entirely invisible to the operator. One machine costs approximately $6 million. Operating economics are calculated in cost per metric ton moved, not cost per hour. The cutter suction dredger. The cutter suction dredger machines the ocean floor. Where traditional dredging removes loose sediment, the cutter suction dredger uses a rotating head to grind solid rock into slurry, then vacuums that material up through a pipe system and pumps it miles away. The largest examples reach total power outputs of 44,180 kilowatts and dredge to 45 meters below the waterline. A ladder extends from the vessel's bow down to the seabed, with the cutter head rotating continuously at the end. This removes rock without explosives, operating meters from inhabited coastline without structural risk to surrounding buildings. Blasting in a working port damages dock infrastructure and is prohibited near residential areas entirely. The cutter suction dredger replaced underwater explosives with precision mechanical grinding. Ports considered too expensive to deepen by conventional means were opened to larger vessels because of it. The crawler crane. The crawler crane at maximum scale carries a rated lifting capacity of 4,000 metric tons, extends a boom over 160 meters into the air, and requires a separate rotating counterweight vehicle connected to its body to prevent overturning under load. The two units rotate together as the crane swings. Without the counterweight vehicle, the boom assembly at full extension would tip the machine before the hook reached the load. Ground conditions are a primary engineering concern. A machine transmitting thousands of metric tons through its tracks into the soil below often requires reinforced piling before it can be positioned. Nuclear reactor modules, wind turbine nacelles, and hydrogenation reactors weighing over 2,600 metric tons have been installed using machines in this category. The operator works in a cab the size of a large office, with views over the job site that resemble an aircraft cockpit more than a construction vehicle. The tunnel boring machine. The tunnel boring machine is a sealed steel cylinder that eats through the earth and assembles its own tunnel walls behind it as it advances, never seeing daylight until it reaches the other side. At maximum diameter, these machines measure over 17 meters across, weigh more than 6,000 metric tons, and generate thrust forces exceeding 80,000 kilonewtons. The cutting head alone can weigh over 2,000 metric tons. An earth pressure balance system mixes a polymer compound into excavated material, converting it into a controlled paste that prevents the soil ahead from collapsing into the tunnel. In urban environments, a tunnel boring machine passes beneath active streets and occupied buildings without disturbing the surface by more than a few millimeters. These machines are disassembled underground at the end of their journey. There is no practical way to retrieve them intact through the tunnel they created. The most instructive failure in the category involved a machine that struck a buried steel pipe casing less than 300 meters into a 3.2-kilometer journey, halted for over 2 years, and generated hundreds of millions of dollars in cost overruns before completing its bore. The dragline excavator. The walking dragline suspends its bucket from a cable hanging off a long boom, swings that cable out over the material to be excavated, and drags the bucket back across the surface toward the machine. The largest examples weigh over 13,000 metric tons, carry booms stretching over 90 meters, and hold buckets exceeding 100 cubic meters per pass. The machine moves on 4 hydraulic walking feet, mounted on an eccentric cam system that lifts the entire frame and shifts it forward in a slow creep. By distributing weight across large pads and rocking forward, it crosses soft overburden without sinking. The largest dragline ever built, operated for 30 years at a single coal mine, then was decommissioned because paying environmental compliance costs to leave it standing was more expensive than demolishing it. The boom was brought down with explosives. People reported hearing the detonation from miles away. The bucket wheel excavator. The bucket wheel excavator is not a machine in the conventional sense. It is a continuous flow system that consumes the Earth's surface without pausing between bites. The largest ever built weighs 14,200 metric tons, stretches 240 meters end to end, stands 96 meters tall, and excavates 240,000 cubic meters every 24 hours, enough volume to fill 96 Olympic swimming pools in a single day. A rotating wheel, 21 meters in diameter, carries 18 buckets at its front, each removing 15 cubic meters per rotation. Material falls continuously onto a conveyor running the length of the machine and out to a spreader depositing overburden kilometers away. The machine never stops to dump or reposition. It moves forward at a rate barely perceptible in real time, powered entirely by electricity through a tethered cable, operated by a crew of 5 people. Its ground pressure across 12 sets of crawler tracks is less than that of a human footprint.